ahead and do an example problem. In this example problem, carbon dioxide enters an adiabatic nozzle. It's going at steady state and it enters in at 1 megapascal and 500 degrees C with a mass flow rate of 6,000 kilograms per hour and leaves at 100 kilopascals and 450 meters per second. The inlet area of the nozzle is 40 square centimeters. Determine A, the inlet velocity, and B, the exit temperature. So again, let's go ahead and start with the schematic. We'll have the entrance of the carbon dioxide as entry at 1 with an exit at 2. Again, we have CO2 gas. And it tells us that entering we have a pressure of 1 megapascal, a temperature of 500 degrees Celsius, mass flow rate of 6,000 kilograms per hour, and an area of 40 square centimeters. It's telling us that at the exit we have a pressure of 100 kilopascals as well as an exiting velocity of 450 meters per second. The next step after the schematic is to go ahead and to draw our assumptions. So, number 1, we're going to assume this problem to be at steady flow. Number 2, we're going to assume that the CO2 is an ideal gas. And like we mentioned, whenever you're dealing with ideal gases, you need to also make an assumption about whether you assume the specific heats to be variable or constant. In this case, we're going to assume variable specific heats. And again, what this basically means is that we're assuming the specific heat to be a function of temperature. And since this is an adiabatic nozzle, there is no heat flow in or out of the system. And also, since it's a nozzle, there's no work interactions. And I'm also going to assume that there's no change in potential energy of the fluid entering or leaving the system. So with that said, let's go ahead and let's do our first law analysis. So we're going to write this in rate form since this is a rate problem. Energy in minus energy out equals change in energy of the system. This is a steady flow system, so the change in energy of the system is 0, resulting that all energy in by heat, mass, and work equals all energy out by heat, mass, and work. So let's write it out. Energy in by heat plus energy in by work plus the sum of all mass flow rates in multiplied by each mass flow rate's enthalpy and kinetic. I'll just write it out as V squared over 2 instead of KE. And potential energy equals energy out by heat plus work out by heat. I'm sorry, work plus work out plus the sum of all mass flows out times each mass flow's enthalpy, kinetic energy, and potential energy. Now in this problem, there is no heat flow, it's adiabatic. There's no work flow, and there's only one mass flow rate, so I'm going to take away the sum sign. And we're going to assume the change in potential energy of any fluid in and out is 0. And there's only one flow in of mass and one flow out of mass, or one mass flow rate in, one mass flow rate out. So those also get canceled out. So all that I'm left with is the enthalpy in plus v squared, or plus the velocity squared over 2n. So the enthalpy in and the kinetic energy in of that one mass flow rate equals the enthalpy out plus the specific kinetic energy out. Now remember, the mass flow is canceled out because work and heat terms go away, and so it's mass flow in times enthalpy and plus kinetic energy equals mass flow rate out times enthalpy and kinetic energy. And the mass flow rates cancel out because there's one on each side of the equation, so they cancel out from each other. So your first law, if I were to put all the terms on one side of the equation, end up being 0 equals delta H plus delta KE. And this is the result of the first law analysis. Now, the problem is asking for two things, right? First, it's asking for the inlet velocity, and then it's asking for the exit temperature. Now, for part A, the inlet velocity, I know that mass flow rate is equal to density times area times fluid velocity flow. Now, if I want to use that to calculate what the velocity is, I get that, well, let me back up a little bit. I know that density is equal to 1 over the specific volume. So mass flow rate is also equal to area times velocity divided by specific volume. So if I take this equation, I can get that the inlet velocity is equal to the mass flow rate times the inlet specific volume divided by the inlet area. Now I have the inlet area, I have the mass flow rate, I just don't know yet what my specific volume going in is. But I know that this is an ideal gas law, therefore I know that this is an ideal gas, therefore I can use the ideal gas law. Pressure times specific volume equals gas constant times temperature. Right? So if I do it all at the inlet, I have the pressure of the gas going in, I have the temperature of the gas going in, and I can use this to solve for the specific volume of the carbon dioxide going into the nozzle, because the specific volume coming out is different because the pressure and the temperature change going out. So therefore the specific volume also changes coming out. But I know what all the properties are going in. So I can calculate my specific volume, plug it in, and I can calculate based on, I'm not going to go through the math in this video, but you can find out that the velocity is 60.8 meters per second. If you went back and calculated the specific volume, you should have gotten 0.146 meters cubed per kilogram. So again, the idea was using the mass flow rate going in, right? You can solve for the velocity, but in solving for the velocity, you don't know what the specific volume is, but you know that this is an ideal gas. So you can use the ideal gas law to solve for the specific volume. And then once you have that, you can go ahead and solve directly for the velocity. Now this problem is eventually asking for what the exit temperature of the gas is. If you go back to your first law, right, if I can use my first law analysis to solve for my temperature. How can I do that? Well, if you remember, for an ideal gas and an ideal gas only, right, enthalpy is a function of temperature only. So in this problem, I assumed variable specific heats. Basically means that my specific heat is a function of temperature. So if I rewrite my first law, 0 equals delta H plus delta KE. What I can do is I can go ahead and I can use table A20. Table A20 is the ideal gas table for carbon dioxide. And if you remember, for ideal gas tables, it shows that enthalpy is a function of temperature only. Now, what I can do is that I know my temperature for the entry for the carbon dioxide entering the nozzle, right? I know that the temperature is 500 C. So what I would do is using table A20, I would find the enthalpy. Now remember, in table A20, it's all done on a molar basis. So the enthalpy and the internal energy is listed as energy per molar mass, not energy per mass. So it's H bar, right? So if I go to the table, and if I look at from table A20, at a temperature of 500 C, which is 773 Kelvin, I can interpolate for my enthalpy, which ends up being 30,797 kilojoules per kilomole. Right, so this enthalpy goes into my first law. Now, remember that using the ideal gas table for carbon dioxide, my enthalpies now are going to be in molar mass terms, which means that here my kinetic energy, right, is going to be in meters squared per second squared. I got to convert that into kilojoules per kilogram, but then I have to convert it from kilojoules per kilogram into kilojoules per kilomole. So I'm going to have to go ahead and multiply by the molarity, right? The molarity I can find in table A1. And you can find that the molarity of carbon dioxide gas is 44.01 kilojoules per kilomole. Now, if I go ahead and take that equation, I can solve for H2. H2 I get equals H1 minus V squared over 2 minus V1 squared, V2 squared minus V1 squared all over 2 multiplied by the molarity. I can go ahead and plug in my numbers where I solve for H2. So that equals my enthalpy at state 1, which I just determined is 30,797 kilojoules per kilomole, plus my velocity out squared minus my velocity in squared. All that divided by 2 is my kinetic energy. Then I convert it from meters squared per second squared into kilojoules per kilogram. Then I multiply that again by the molarity of carbon dioxide gas, which is 44.01 kilograms per kilomole. And then I can solve directly for H2. I get a value of 26,423 kilojoule per kilomole. And then from table A20, for a value H2, for a value H2 of 26,423 kilojoules per kilomole, you can find that the corresponding temperature for T2 would be 685.8 Kelvin. Now that is the answer for this problem, assuming you account for the changing specific heats with temperature, right? If you remember, the ideal gas tables give you values of enthalpy and internal energy for changing temperature, which also accounts for the changing specific heat. But what if we were to go ahead and just try to resolve this problem for constant specific heats, right? How does that change how we approach this problem? So again, this is assuming that specific heat is not a function of temperature. So if you remember, back to our first law, we had 0 equals H2 minus H1 plus V2 squared minus V1 squared divided by 2. If we were to assume constant specific heat, we would substitute delta H as Cp times T2 minus T1 plus V2 squared minus V1 squared over 2. And what you would do is, at this point, is just solve directly for T2. So you get that T2, So what you would have at this point is just solve it directly for T2. Now, the question always comes is, okay, well, how do I substitute Cp delta T for delta H because my Cp value is constant, right? I don't have one value of Cp at T1 and another value Cp at T2. They're the same between T2 and T1. And usually what we would do is that we would find Cp average between T1 and T2, right? So I would take the Cp at T1, and then I would go ahead and also look up the Cp at T2, and then I would take the average between the two. But in this case, I can't do that, right? And the answer is, why can't I do that? Well, it's because I don't know what T2 is, right? I know what T1 is. So what do I do when I'm trying to do average specific or constant specific heats, and I don't know what both temperatures are? Well, what I'm going to do in this case is I'm going to take my Cp at T1, right? All I know is T1, so I'm going to go ahead. I'm going to look up on table A2. I'm going to look up on table A2 the value of Cp corresponding to a temperature of 500 degrees Celsius, because that's the only temperature I have. So if you go ahead and look that up, for carbon dioxide, you would get that it is 1.155 kilograms Celsius per kilogram Celsius. Now, again, usually it's the average Cp between T2 and T1, but I only have T1, so I'm going to go ahead and find the Cp at T1, and then I can go ahead and use the other knowns of the problem to solve for T2. And if I assume constant specific heats, I get a temperature of 687 Kelvin for constant specific heats, whereas I had a value of 685.8 Kelvin for variable specific heats. So the answer is not much different, and whether you assume constant variable specific heats is usually up to you. You can pick one or the other unless the problem statement specifies one or the other.